Well, hello. Um, Today I would like to have a short explanation about isomorphisms with is chapter 9E section 2. Now, the first thing we are going to have a look at is what is an isomorphism. Um, well, the point is I start with two groups, and what was a group again? It was the combination of some kind of set, G in this case, and some kind of operation. And then under certain conditions, the associative law, for instance, need to be applied, then we call this a group. And I have another group, like a set H and another operation which I call circle. And now these two groups are isomorphic if the following is true. First of all, there need to be a relation F between G and H where this relation is bijective. And secondly, this bijective relation F needs to be like this if I apply this operation star on two elements of G, A and B, so A star B, then this must be the same as the function applied on A, circle operation function on B. So if I have here A star B, then it must have the same result as the function of a circle FB. Okay, now let's have a look how this now looks in praxis. I have two groups. I have R plus, the positive real numbers, and the multiplication, the simple straightforward multiplication. That's one group, and I have another group with all real numbers and the simple addition. Now, are these two groups now isomorphic, yes or no? Now, first of all, and of course I need to define a relation, and the relation is the log. Okay, so let's have a look if we can understand this. I have here all the positive real numbers like 0.1, like 1, like 10, and so on. And I have here a set of all real numbers, and the relation is the log. So for instance here the image will be 1, the image will be 0, -1, and so on. So indeed this is a bijective relation, that's clear. Secondly, the second demand is the following. I have this function, and this function applies, or relation rather, applies to the star operator, and it must have the same result as if I apply the relation on A, circle operator, relation on B. And is that true in this case? Now, if I have two originals, A and B, and the function or relation, function in this case, is the log, then the log of A, and what was the star operation? The star operation was the simple multiplication. Is that then the same as the log applied to A, and the star operation in this case was the plus log B? And of course that is true. So therefore we have here an isomorphism. Now of course you could ask yourself, why on earth would this be helpful? What does it bring us? Now, one of the reasons you could use isomorphisms is the following. You have an area of math which you're quite familiar with, and you know all the properties and everything, and you're quite happy with that. But you want more. You want to discover a new area of the mathematics which is relatively unknown, and well, you don't know that much about it. Now, what you can do, of course, is try to prove all the properties you want to have, like associative law, commutativity, and so on, in this new math here, which is in fact a lot of work. There's another way to incorporate all this new math you are discovering at the moment, by saying, okay, I have here a set of properties that I know, that I'm aware of, and those are proven. So this is the known territory. Then if I can prove that these two form an isomorphism, then all of a sudden, where these properties are preserved, then all of a sudden I know that all these properties here are also known. And I can simply apply all my knowledge from the previous math to the new math, which saves me a lot of work. Now, isn't that great? Now, I want to give you one more example, and this example comes from page 150 of your book, and it's about the set Z5, the first 5 elements of set, without the 0, which leaves me with the numbers 1, 2, 3, and 4. And the operation I use is multiplication modulo 5. That's my operation. And the question is now, is this a group? Yes or no? That's the question. Now, first of all, to have an idea of what we're talking about, let's have a look at the Cayley table. This is the multiplication modulo 5. Here I have my elements. And for instance, 2 multiplied modulo 5 with 4 gives me 8. If I divide that by 5, the remainder equals 3. So that's my answer. For instance, here the remainders are 1, 2, 3, 4 respectively, and here also the same. Now 2 times 2 is 4, divided by 5, remainder is 4, and 2 times 3 is 6, remainder is 1, and so on. And if I fill out the table, it goes like this. Here I have a 3, and here I have a 1. And obviously I see already a symmetry, a beautiful symmetry in this Cayley table. Now, if I want to know if it's a group, yes or no, I need to clarify a few things. First of all, I need to clarify closure. Then I need to clarify associativity. Next, I need to clarify the identity. And last thing is then the inverse operation. Now, first of all, let's have a look at closure, which means I have an element of A of the function, for instance, the set, for instance, 3. And if I multiply modulo 5 this with another element, for instance 2, then the result needs to be again an element of Z5 without the 0. And of course that's obvious, because here all these numbers I see here are the numbers 1 to 4 without any exception. So all results are an element of this set I started out with. Associativity It's logic because we are talking about integers, and we know that for integers it is true that a times b gives the same result as b times a, so therefore this is also true if I multiply modulo 5, so therefore associativity is also done. Then the identity, well, it shouldn't be a surprise because I multiply. The identity is 1 if I have, for instance, an element a, and I multiply modulo 5 this times 1, then this gives me the same result, being a. Obviously, because a times 1 is a, so there you have it. And of course you see this here also, that is true. So identity is also okay. Then the inverse, well, if I have 1, with which element do I need to multiply this to get my identity 1, which I just discovered? Well, obviously from the Cayley table, that is, the identity is then 1 itself, so it is its own inverse operation. And with the number 4, with what do I need to multiply modulo 5 the 4 in order to have my identity 1? Well, you see, 4 times modulo 5, 4 gives me 1, so I can say that 1 and 4 are their own inverse operations. Now if I look at 2 and 3, you see the ones over here, and so if I have a number 3, what would be the inverse operation if I want to get to 1? It's multiplying by 2, and of course the other way is true as well. I have to multiply with 3 to find the same identity. So 2 and 3 are each other's inverses. So we can conclude that this is indeed a group. It is a group. Yes.